Okay, so now we're going to take all of this stuff about metric and apply this to the scientific method. Okay, well, before we get into that, let's go over a couple of vocab words. So a fact is a close agreement by competent observers who make a series of observations of the same phenomenon. So, competent observer needs to have some background on the subject, and they all make similar observations independently. A hypothesis is not a fact. Okay, a hypothesis is a prediction about a situation that is presumed factual until it's demonstrated otherwise. So we've made this series of observations about the same phenomenon. We make a prediction, that it's going to follow that same pattern every time. We presume it to be factual until, for some reason, it is demonstrated to not be true through some experiment. Okay, and then sometimes these can become laws. So a law is a hypothesis that has been tested over and over again, and no contradiction has been found. Okay, from here we kind of have a theory. So a theory is a body of knowledge and the hypothesis about some aspect of the natural world. Theory of evolution is one. That's quite popular and controversial. Okay, and to get all of these facts and this data and all this collection going, we have to employ the scientific method. So this is a method that is extremely effective in gaining, organizing, and applying new knowledge. And in fact, you probably use the scientific method all the time in your daily life. You just don't stop for a minute and say, hey, I'm using the scientific method. Okay, but if your car doesn't start or, some random issue like that comes up, you probably are employing the scientific method in order to solve that problem. Okay, so let's talk about what those steps are. First, you have to recognize the problem. So let's say it's that your car won't start, or your mechanical pencil doesn't work, which always seems to be my problem. So I recognize that as a problem. I make a hypothesis. So let's say I assume that the lead is stuck on the tip of the pencil. Or for the car, if you're knowledgeable on how cars work, maybe you could come up with some reason why maybe you think it's not working. Then you predict the consequences of your hypothesis. What do you think is going to happen? And then you perform experiments to test your predictions. Okay, so when we talk about experiments, we're going to talk about the independent and dependent variable, and also making sure that you only test one variable at a time. Okay, so all of those things go into experimenting. Once you have done your experiment and you have collected your data, you try to come up with a rule about your data. And it has to organize the three main parts. It has to organize your hypothesis, has to go along with your prediction, and then what's your experimental outcome. So does your outcome support the hypothesis? Does it not support the hypothesis? And what are you going to do next? Okay, well, along with science also comes technology. And although they are related, they're not the same thing. So science deals with knowledge for its own sake. So this would be like going to college and getting, a degree in physics. You have this physics knowledge. Technology is an application of scientific knowledge. So a lot of people would say that that's what an engineering degree is you're taking that scientific knowledge and now you're applying it. So for example, a mechanical engineer takes all of that knowledge and applies it to the building of a vehicle or something like that. Science deals with theoretical questions, whereas technology deals with practical problems. Okay, last part of collecting data and doing the scientific method is measurement. So this is a comparison between an unknown quantity and a standard. So if you're measuring the length of something, you're using your standard, which is a ruler, and you're trying to measure the length of, let's say, a book or some unknown quantity. Okay, these results are often reported with some amount of uncertainty, because everybody's going to look at that ruler and read it just a little bit different. So if, let's say, 10 people measured the length of a book, if those uncertainties overlapped, then we would say that those measurements confirm each other. So for example, we have 14.6 plus or minus 0.2, and so that means that it really could range from 14.8 to 14.4. 14.8 plus or minus 0.3 could go from 14.5 to 14.11. Yeah. And then 14.0 plus or minus 0.1 will go from, where's my pen? 14.1 to 13.9. And so let's see, we had what? 14.5. No, I did it backwards. To 15. Well, if we go on a 10-point scale, let's just 14. No, it should be 15.01 or 0.1. Sorry, 0.1. And then 14.6. So 14.8 to 14.4. Now, these two, their numbers overlap. But if we look at the 14.0 plus or minus 0.1, they don't overlap, and so we would say that this one is not a valid measurement. Okay, so along with measurement is precision versus accuracy. Okay, so precision is the degree of exactness of a measurement. How close are the measurements to each other? So let's say that, the common example is to shoot arrows at a bullseye. So let's draw our bullseye. Let's say that you shoot 3 arrows and they're all really close to each other. We would say that that's pretty precise. You hit the same spot almost every time. So if we had 14.6 plus or minus 0.3 versus 14.6 plus or minus 0.1, 0.1 is a smaller degree of variation, and so it's more precise. This depends on the instrument and the technique. So, your technique, if you're shooting all of your arrows over here, maybe you just need to change your technique a little bit to get onto the bullseye. As far as instruments, graduated cylinder versus a beaker, graduated cylinder is going to give you more measurements, so it's going to be more precise. And this precision is also determined by the number of significant figures. We're not going to deal too much with significant figures in physics. Okay, the second part of measurement is accuracy, and this describes how well the results of a measurement agree with the real value, or the standard. So let's say that we shoot an arrow, and it hits right on the bullseye. We would say that that was accurate. Now, what you really want is something that's accurate and precise, both. And so something that's accurate and precise would probably have all 3 really on the bullseye. Okay, so this would be both. Let's say you had one here, and one here, and one here. Well, this one might be considered accurate, but these aren't. This might be neither. Okay, so what you really want is all of them at the standard and all of them together. Okay, so our third section is graphing data. So we're going to take our scientific method, collect our data, figure out how to measure it, and now we want to graph it. The first thing we need to do is identify variables. So the independent variable is the factor that is changed or manipulated in an experiment. It's what you are controlling or what you're changing. Dependent variable is what gets changed because of the independent variable. So it depends on the independent variable. So for example, let's say we have this spring and we're placing masses on the bottom, so we're stretching the spring out. Well, what we're changing is the mass, and so that's the independent variable. And then what's changing because of the mass is the length of the spring, and so that's the dependent variable. And so what we would do is take different masses, measure the length, plot those points, and then draw a line of best fit. And so let's say we have our graph, and let's say that as mass increases, length increases. So let's say we have points like this. Well, that's a line of best fit. We're kind of trying to figure out how to go through most or all of the lines. Okay, well, we would say that that was a linear relationship. And so linear relationships follow the form y equals mx plus b, which is the equation for a straight line. So m represents our slope, which is rise over run, so change in y over the change in x. And that b is your y-intercept. So if this is our graph, and here's our line, then this is our b value. Figuring out how much it changes with y over x, that's our slope. We also have 2 different kinds of nonlinear relationships. The first is quadratic. So here the equation is y equals ax squared plus bx plus c. And what this means is that one variable depends on the square of the other. So if we had here's our graph, a quadratic might look like this. Okay, it's not a linear relationship. The last type we're going to talk about is an inverse relationship. And so you'll notice that the y is on the top of a fraction, or the numerator, and x is the denominator. And so what this means is that one variable depends on the inverse of the other. And so if we were to draw a picture of that, it would look like this. So here, as one of these is our y variable is increasing, our x value is small, and as x gets larger, y gets smaller. So they're inversely related or opposite. All right, so that takes us through chapter 1. Pretty short. We'll do some practice and some labs and discuss any questions you have in class. Have a good day. Okay, so here's your check for understanding for section 2. So in this section, we talked all about the scientific method, independent and dependent variables, and graphing. So number 1, describe an example of how you have actually used the scientific method in real life and highlight the specific steps. So don't think about a lab that you did, but just think about some problem in your life that you solved using the scientific method. You probably didn't even realize it at the time. Number 2, come up with your own example to explain the difference between precision and accuracy. And number 3, explain the difference between an independent and a dependent variable using an example of your own choosing. All right, we'll discuss these in class. Have a good day.